Hello, we are FTC Team 8300, the Pyro Eagles from Shelby, North Carolina. Our ultimate goal robot is a dead-axle mecanum drive with a pass-through intake and shooter. This design has proved to be very reliable and has extremely few moving parts. Our intake is a two-stage flip-out where rings are initially pulled towards the robot using fast-fitting garage door sealant. Our flip-out intake spans the width of our entire robot to increase the surface area which we can collect. Once rings travel into the robot, we have a double roller system that moves the rings into our hopper. From here, we use a Go Build a Super Speed servo which we use to launch the rings into our flywheel. Our wobble goal mechanism uses a long arm that allows us to reach over the wall, allowing us to cycle wobble goals much faster than we would otherwise. Our mechanical design process emphasizes hands-on prototyping, but uses a significant amount of computer-aided design using Onshape and MATLAB. We use Onshape to design parts and ensure compatibility once assembled, and we use MATLAB with SimMechanics and Simulink library to characterize our mechanisms. This allows us to run simulations of subsystems and control systems interacting with one another and ensure that components will behave stably on the real robot. For software this season, we began our drivetrain code with a basic go-to-position algorithm that uses 3 PID controllers to control our mechanism drivetrain's X, Y, and theta axes. The PID approach worked well for most cases, but was not robust to disturbances such as other robots colliding with ours. In addition, set point changes would cause a significant acceleration to occur. This large acceleration could cause inaccuracies with our odometry, and therefore we needed a better solution. This was when we discovered the linear quadratic regulator and full state feedback control. Full state feedback is a feedback controller similar to PID control, but with the difference that we instead feedback every state of our system. For example, with our mechanism drivetrain, we feedback our X, Y, and theta position, as well as the rates of change for each. This set of states is called our state vector. In addition to our state vector, we also have a gain matrix known as K. This gain matrix takes the place of Kp, Ki, and Kd of the PID controller and is what we are tuning. Full state feedback is essential because it allows us to move our system's eigenvalues anywhere in the complex plane. We find the eigenvalues of a plant by deriving a state space model and then finding the eigenvalues of the A matrix. If all of the system's eigenvalues are in the left half plane, then our system is stable. Still, if any of our eigenvalues are on the right of the imaginary axis or the origin, then our system will be unstable. This problem is where full state feedback comes into play, as we can move these unstable eigenvalues into the left half plane, thus making our system stable. Now that we know how full state feedback works, we need a way to find this value of K. We do this using the linear quadratic regulator, or LQR for short. The linear quadratic regulator turns the problem of finding our gain matrix into a quadratic optimization problem. We tune two matrices, Q and R. Large values of Q penalize steady state error, and large values of R penalize actuator effort. After initializing Q and R, we then solve the discrete time algebraic Riccati equation, which lets us directly solve for K. This methodology is far more intuitive than tuning a PID controller. Also, assuming our system is observable and controller, LQR will guarantee stability. We also use our linear quadratic rig for our drivetrain in combination with trapezoidal motion profiling to follow smooth trajectories. In addition to using these on our drivetrain, we also use a linear quadratic regulator for our wobble goal arm and shooter flywheel. For angle measurements of our drivetrain, we have also developed a custom Kalman filter. This can also be called a linear quadratic estimator by some, to obtain the optimal estimate for our angle. The Kalman filter works by using an estimate of our drivetrain's angle, in this case the long robotics analog gyro, and the second measurement, which is our dead wheels. The Kalman filter will then use the same discrete time algebraic Riccati equation as our linear quadratic regulator to solve for its own value of K. This value of K in a Leuenberger observer allows us to achieve an optimal state estimate, and according to the original proof by Rudolf Kalman, will eventually compute the actual estimate of the system.